All right, thank you. Let me just try to turn on my camera here. Very good. Welcome to this talk on shortest path in Portalgons. My name is Maarten. I'm in Utrecht, as you can see, and this is joint work with Frank and Rodrigo. So, Frank, are you here?
Yeah.
Welcome. So good of you to join us. And then our third co-author is Rodrigo. Rodrigo, do you read us?
Hey, hi, I'm Rodrigo. Nice to see you.
Welcome. So Rodrigo is joining us straight from sunny Spain.
Yeah, cool technology you've got here.
Yeah, indeed. So, shortest path in Portalgons.
So you may be wondering what a Portalgon is.
Yes, I was wondering because the name sounds a bit silly, I would say.
Well, it's actually quite simple. It's a polygon, or rather a set of polygons.
Fragments.
Which some of the edges are identified.
And these edges are the portals. So you can see in my fragment, there are 3 portals. There's a purple one here, a blue one here, and a green one up there.
Yeah, so I also have one of these green ones over there, and 2 red ones at the top, and an orange one. And so the trick is that locally around these portals, space is just a 2-dimensional Euclidean space. So you could actually go through one of these portals and never even realize.
Wait, I also have a blue portal here. So are you telling me that if I would put my hand through this portal, it would come out on the other side?
Yeah, exactly. Go ahead, try it.
You sure? Sounds scary. Is it dangerous? Oh, wow. Hi, Martin.
Hi.
Awesome.
Yeah, so since the space is locally Euclidean everywhere, a Portalgon actually represents some sort of underlying space, and we're interested in this space.
Well, but why do you want to study this anyway?
Well, so Portalgons are a natural generalization of polygons, but also, for instance, of polyhedral surfaces. So they're interesting to study from a theoretical point of view.
Actually, I can also see some practical applications of this. So suppose for some reason that, let's say, we want to see our friends, but international travel is restricted. And then at least we could use this to, give each other some, I don't know, oranges. Do you have some oranges?
Really? Yes, you want an orange? Sure. I have one. I'm in Spain, so.
Oh, thanks. Nice. Thank you.
Yeah, so apart from that, Portalgons actually also show up in the apparel industry.
Yes, believe it or not, it was the original motivation for this work, designing clothes.
Yeah, so good. So now that we actually know what Portalgons are, let's actually start the fun part and see if we can actually compute with these Portalgons.
In particular, shortest paths.
Yes, but what's the shortest path like in a Portalgon?
But it's just the shortest path, right? Just like in a polygon, except that it can go through portals.
Right. So say if I wanted to go from me to you, then I could go on this portal that we saw before, but I could also try this other portal on top of my head. Is it good? Here we go. Yeah. Oh. And that may be shorter. I don't know.
Right.
So computing a shortest path or finding the shortest path is not obvious since there's multiple routes from A to B.
Yes. So, but then how can we compute these shortest paths in Portalgons?
Yeah. So one option would be to sort of adapt algorithm that works in polygons. For example, continuous tag-string.
Right. It's the one where you grow these circles, right? You keep track of this wavefront as you approach.
Very cool.
Yeah, so, I mean, that sort of works, but the question is, so how long does it take?
Right, because every time you hit one of these portals, now you also have to spend time on that.
Yeah, so often can happen that you hit a portal.
Yeah, even actually a single line segment can actually already pass through a portal multiple times.
Really?
Oh, watch it. Ah, I see. So you're moving now through the red portal, I think twice, yeah. Oh.
Nice. Oh, it's coming up here, I think.
Yeah, so that's interesting, right? So that means we might not even be able to bound the number of times that this happens, or at least not as a function of the complexity of the input.
Indeed, if Frank's chimney was longer and the stick would also be longer,
then this could happen, I don't know, an infinite number of times?
right. So basically the complexity of the shortest path would not be bounded. But that would be a bit sad.
That's pretty sad, yeah.
Why does Frank always have to go and win things for us?
Yeah, actually, Frank, it's because you have this strange, long, thin chimney on your fragment.
Right, Frank, why do you have a long chimney?
Well, I mean, I didn't design this thing.
I have to say that my fragment looks much nicer, has a better shape. I would say mine is a happy fragment.
What do you mean, happy?
Well, my fragment doesn't have any long and thin parts, so no shortest path, I think, will go through it many times, as happens in yours.
That's a good point, right? I mean, so suppose that no single shortest path goes through a single fragment more than a constant number of times, then we could call it a happy fragment.
Uh-huh.
And if all fragments of the whole Portalgon are happy,
well, I mean, then we can compute shortest path in polynomial time.
Then everybody's happy. That's so cute. But what if not all fragments are happy?
I mean, maybe we can make them happy.
How can you do that?
Well, I mean, if what we care about is somehow this underlying space that the Portalgon represents.
Yeah, that's the same. Yeah.
Well, not really. So, in fact, we can actually transform our current Portalgon that we're in into a Portalgon, an equivalent Portalgon that is actually happy.
Ah, nice. But you're changing the Portalgon, right?
Well, I mean, so the underlying space is somehow still the same. So shortest path is between any pair of points actually still has the same distance. If I use this stick again, then hopefully see this.
you have to aim a bit higher. Yeah. So it's indeed. It's going through the portal.
Yeah.
So now this red line is not a portal now, right? It's just a fragment.
Nice.
So is this always possible? This kind of rearranging trick that you did there?
Yeah. So we conjecture that for every Portalgon, it is possible to find an equivalent Portalgon that is happy.
Oh, that's a very nice conjecture. But so what are our results? Is there anything we can actually prove here?
Yes. So if the Portalgon consists of a single fragment with only one portal, then we can actually prove the conjecture.
Impressive.
Yeah. Well, actually, I mean, we can prove the conjecture for a slightly larger class of Portalgons, depending on their fragment graph.
Fragment what?
Well, so it's a graph that has a vertex for every fragment and an edge for every portal.
Right. So you mean a multigraph, right?
Why is it a multigraph?
Well, remember we have these two portals that are both going between our two fragments.
Right. Yes.
And actually, if you look at this portal there in Frank's fragments, then that's going from his fragment to his fragment. Right?
I see.
Yeah, so if the fragment graph is a tree, or if it has only a single cycle, then we can also prove the conjecture.
Very nice. And what about the other cases?
Yeah, I mean, they are open.
Okay, so I think we might just have enough time to say a few words about how we prove the conjecture in the very simplest case, which is when we have two parallel portals.
Yeah, so when two of the edges are parallel, then what we can do is somehow take their starting points and project them onto a parallel line and look at the distance between these starting points. And we call that the shift of the portal.
Right. So right now the shift of your chimney is like one chimney width.
Mm-hmm. Yeah, indeed. So in this shift somehow models the distance along the portal that you teleport if you use it once.
But when we reconstructed your chimney, Frank, the shift became 0, right?
Mm-hmm. Yeah, indeed. So the transformation is actually aimed at somehow reducing the shift of the portal.
Okay, because having low shift is good then.
Mm-hmm. Yes. So if the shift is 0, then you actually never pass through a portal consecutively.
I see, because basically then it will be shorter just to move directly along the portal than going through it several times.
Yeah, exactly. And so now we can actually show that we can always transform a fragment in order to make this shift 0.
And that's nice, but I don't think we have time to show that anymore.
Yeah, we should stop pretty soon.
But there's so much more to say.
There is, yeah. So Portalgons are quite fascinating, and there are many interesting questions to open about them.
So if you want to know more about them, join us in the poster discussion. I will bring orange for everyone.
Oh, nice. Thanks.
Thank you for watching. We'll be happy to answer any questions that you may have.